Okay, guys, term 2, final physics vid. So, chapter 1 and chapter 2, they're in the term 1 vid. So, now I'm just going to do chapter 3, 4, 6. Okay, here are the formulas for chapter 2. You guys should know them, all of them anyway. Yeah, these are the electricity forms. Okay, let's start. So, magnetism, yeah. So, magnets, why are they magnetic? Basically, because their magnetic domains, or like the electrons in some way, are lined up. The oh, what? Why is it this big? What is? Okay, the magnets, whoa, the magnets in some way, their magnetic domains are lined up. But what does that mean? Each magnetic material is made up of a bunch of small, tiny magnets. Yeah. So if you were to cut a magnet, you'd have north, south, north, south, north, south, and it goes on for the whole magnet. You can cut it even more, you're gonna have north, south, north, south. And a magnetic field, it travels from the North Pole towards the South Pole. But inside the magnet itself, it's going from the south, this would be the south, this would be the north. It goes from the south to the north inside the magnet itself. This would be going like this, and you'd have multiple field lines. And this is how it would go, basically. So here in the quiz, this question, it's talking about like if you cut a magnet, you'd have north, south, north, and it would go so on as you keep cutting it. Okay? Now these lines outside, or these are the flux patterns. There is different like types of flux patterns. Now, let's say you have a bar magnet, be north, south. The flux patterns would just look like this, and they would go on. There would be more flux lines tighter together if it's a stronger magnet. The flux pattern for a horseshoe magnet, for example, would be like, wait, let me just draw it first. The horseshoe magnet would have a north pole, a south pole. In the middle, it would be going straight from the north to the south, and then it would be curving like this. If you guys remember how the electric field was, it's basically the same thing, but you can say the north is the positive in the electric field and the south is the negative. Okay, now what if you have two magnets attracting, so a north pole and a south pole? How would the magnetic field lines look like? They basically look like this. You'd have north going to south, and then it curve and go around. What if they're repelling? But we'll also go around that way. What if they're repelling? Let's say I have a north and a north, or a south and a south. So here, the magnetic field lines would repel. They wouldn't touch each other. And you'd have a spot in the middle of the two magnets where there is zero magnetic force. It's like a dead spot in the magnet. Okay? There's also another case. Let's say you have two magnets side by side. Let's say this is north, this is south, this is north, this is south. Oh no. Like this, it would go straight from north to south. You just have these two sides attracting and these two sides attracting. But what if it was north, north? So this was north, this was north, this was south, this was south. This question came in one of the periodics, by the way. It was like this. So you had north, north, like this type of setup with two magnets. And they were asking, where are the magnetic field lines the strongest? And they were like labeled to 1, 2, 3, 4 in ascending order. So here, perfectly between the two norths, you'd have a dead spot. I don't know how to draw it. Like here, there'd be no force, and between the two souths, there would be no force. Okay, I know I drew the lines a bit weird, but there would be no force perfectly between them, and it would be the strongest here, right in the middle of the two magnets, because the two norths are going towards the two south. Oh my god, here. So here it would be the strongest, And then the rest, obviously, it's stronger near the poles, so kind of stronger. And then it's weak out here, like maybe here would be 3. But this, between the two norths and between the two souths, this is a neutral spot. There's no magnetic force. Okay? So now I'm gonna go to question 10. Okay. The direction of the force on the compass by the magnet. Okay, so the magnet is gonna go from north to south and from north to south. So here it's going like this. So that is to the right. If this was the south pole, the magnet would point towards the south pole. So this would be rightwards. It's gonna go this way. Okay. The net force by magnets on the plotting compass is now here. In this case, it's between two same poles. Okay. So here there would be no force, so it's gonna be 0 meganewtons. Now question 19. Something came like this in the periodic. You guys should know this, especially with the two magnets next to each other, the north, north, south, south. That one came in the periodic. Okay. So point A, it would be the weakest. They said name the strongest one, so point A would be the weakest because it's between two similar poles. The force at it is 0. So here it would be 4. B is next to the pole, so it's the strongest. So 1. C is closer to the magnets, but still not the strongest. 2. And D is the furthest away. So 3. Okay. Now there's more stuff. Okay, now here it's the thing called magnetic shunting or magnetic shielding. So what is that basically? Let's say you have a magnet, basically a north and a south pole, and you place a soft iron near it. That soft iron would kind of absorb the magnetic field. So instead of going normally like this and like this, it would go through the soft iron. So it would go like this, through the soft iron. The soft iron would kind of like take them towards it. I don't know how to explain it, but this is what it would look like. This is called magnetic shunting or magnetic shielding. Also, this thing, if you want to protect something from a magnetic field, so let's say you have this let's say this is a south because I need space for where the magnetic field lines are. North and a south. And you have an object, let's call it, or it's what they call it in the English. And you want to protect this object from the magnetic field. You place a soft iron around it. It's like a soft iron ring. Okay, it's a ring. The magnetic field would come out of the north. And it would be absorbed by the soft iron. And then it would be deflected away radially. Okay, from the soft iron. Protecting ore, which is inside. Okay? Now, also there's this thing called superposition in a magnetic field. Let's say you have two magnetic field lines. One is going like this, one is going like this. It won't work. You can't have two. So they would just turn into one magnetic field, and it would be like basically the sum of the two vectors. So here I'm gonna solve CQD's number 9. Where's number 9? Okay. A magnetic field V exerts a force of 3 newtons to the north on a given magnetic pole P. So here, here let's say, what did they say? A magnetic force B, 3 newtons north of P. So let's say here you have P. Now 3 newtons north. So there's a magnetic force. There's a magnetic force here. And another force B prime exerts a force of 4P to the east. So 4P this way. A, find the direction of the resultant force of if P is a north pole, and find the resultant force if P is a south pole. So P, if it's a north pole, then it would point towards the magnetic field, so it would be the resultant force. So let's say here, this is the x-axis, this is the y-axis, this is perfectly north, this is perfectly east. So P would be like this. They said find the direction, but if you wanted to find magnitude, it would just be like 3 squared plus 4 squared. The magnitude would be 5 newtons. And to find the angle or the direction here, you just do shift tan opposite. So 3, let me use the y so it can be clear. 3, because it would be the 3. Oh, it's not clear, let me use the red. 3, and this would be the 4 newtons. So shift tan opposite, so 3 over 4. So it's going to be east 37, because shift tan 3 over 4. I think it's 7. Shift tan 3 over 4. It's 36.8, so yeah. 37 degrees from east to north. And if it was the south pole, so it would point perfectly in the opposite direction. Its magnitude would also be 5 newtons. But since it's perfectly in the opposite direction, this would also be 37 degrees, and you would have west 37 south. Okay? And I'll solve question 10 also. Define a magnetic field and identify its direction. Okay? A magnetic field is the area around the magnet where a magnetic force is applied. Okay? Its direction is the direction of the force produced at a north pole. So if you place a north pole at that point, the direction that north pole points is the direction of the magnetic field. Okay? Now, what are some uses of these magnets? Okay, now these are kind of annoying, but oh well, what are we gonna do? First, you have the what was this? The current meter. So you have the current meter. It looks something like this. Wait, what? No, how do you do something? Something like this doesn't matter. Okay, this is this is table. Wait. So here you have basically a horseshoe magnet. Yeah, something like this. Okay, here you have a north pole side and a south pole side. In the middle, you have a soft iron. Okay, so how would the magnetic field lines go? They would go from the north into the soft iron and towards the south. They would look like this. This is a current meter. You don't need to know how it measures current exactly, but it's a current meter. And you should know the current meter. They ask about this, and it's an annoying question. Is it plane symmetric or axially symmetric? They like to compare it with the loudspeaker. This is the loudspeaker. You have a south in the center, and you have like a ring magnet, a north pole around it. The lines are going like this. So here, this is the current meter, this is the loudspeaker. Loudspeaker. Okay. So here the magnetic field lines are going from north to south. This is plane symmetric. If you slice it in the middle, this side would be symmetric with this side. If you slice it with a plane, this side would be symmetric with this side. So that's what they mean plane symmetric. This one is axially symmetric. Why? Because let's say this is the axis. They're surrounding it in a circle. Here it's just going from right to left. Here it's around it in a circle. The axis is like a line going through the south, through the middle magnet. Okay? We don't need to know how they work really, but they like to ask questions about them, and it's kind of annoying. And there's questions in the 3.6, the 3.7 to 3.10 quiz. So let's just go to that one about these two, and I think they would bring something about these questions. Physics. So wait, 3.7. Well, I think it's 3.6. No, that's applied math. Wait. 3.7 to 3.10. Okay, so it's question 6 and 7. Okay. Radial fields are fields which weaken away from the center and remain uniform at a constant radius from the center. Oh yeah, bro, guys. They're both radial fields. You should know this. Both are radial. Okay? Radial fields are both of them. This is a plane symmetric radial field. This one is an axially symmetric radial field. Okay? Select the magnet which produces an axially symmetric radial field. It's this, and it is the loudspeaker. And question 7, it's this, which is the current meter. And plane symmetric radial fields are used in electric motors also and the current meters. Okay? Now, magnets, they can also get demagnetized. How would they get demagnetized? Right, we said inside the magnet, there's a bunch of, like, the magnetic domains are lined up, which are basically some electrons lined up in a specific way. So, how would they get unaligned? Let's say I knock the magnet on a table or I drop it from a height. So that would, like, shake everything. So either by dropping or knocking. I'm not gonna write the whole thing. Knock. Okay, dropping or knock. Heating it, because the electrons would move everywhere, and maybe the metal might even melt. So heating it. Or placing it on an alternating current. Through an alternating current, because the alternating current changes directions a lot. It would mess also with the electrons, so alternating current. Also, if you store it without soft iron keepers, why would storing it without soft iron keepers make it lose its magnetism though? Because inside the magnet here, it's north, right? If we split it a lot, this is just the north pole. So these north poles, they're repelling each other. This is repelling this. There's like small repulsion inside here. So the soft iron keeper helps protect it from that. Okay, they don't repel each other that much. If you place, there's an experiment in the book. If you place a bunch of needles all stuck like this. Oh, no, haven't you? A bunch of needles like this. These needles would start repelling each other. Okay? They would all repel each other. So that's what's happening here. That's why you need to store them with soft iron keepers. Soft iron. Okay? Now, we know that magnets generate a magnetic field, and the domains of the magnetic field have to be lined up, which are basically a small electron. That means that a current can generate a magnetic field also. Let's say you have a wire, a straight wire, current is going through it like this. So it would generate a magnetic field around it. The magnetic field around it in here, in this case, would be going like this. And here, we start using what? Wait, I think, wait. I think the lines are going in the wrong direction. Wait. So, if it's going up, how do we find the direction of the magnetic field? The good old right hand rule. This is the one where you curl your fingers, because it's a straight wire. Your thumb, you point it with the wire, and you curl your fingers. That would be the direction of the magnetic field. So yeah, I did what's it called? I drew the first time wrong. It would be going like this. The current is going up, so you'd curl your fingers, and it would be going like this. Okay? It's called the grip rule. Oh yeah, you guys need to know the rules. There was once a CA where they asked, well, what are the rules? Yeah, you don't need to use them to solve for the direction, but you should know that there's one called the grip rule. Grip rule, which is the one I just did now. You point your thumb with the current, and you see the way your fingers curl. That's the magnetic field. There's also Maxwell's screw. Maxwell's screw. That one, you imagine a screw. You put it in you put it with the current, let's see, this is the screw. You put it with the current and it rotates to the right, so it would rotate like this. It's kind of annoying. We don't need to use it yet. They might ask, like, let's say you have a screw and you rotate it, what rule is that? It came something like that in a CA before. That's, you just need to know that. Okay. Also, let's say you have the wire is a ring. Let's say the wire is a ring. So then how would the magnetic field through it go? Say this, there's a current flowing through this ring wire. Current flowing like this. So here, you can basically put your thumb with any of them. I'll still use the grip wheel here. So let's say I put my thumb here, it's going like this. And here it's be going like this. And here it's be going. So basically it's coming towards us. The magnetic field is coming out of the plane. The magnetic field is like coming out of the plane, so it's a dot. So now this magnetic field, the side coming towards us, so where the magnetic field is coming out from would be the North Pole. We'd have a North Pole coming towards us, and into the plane, that's the South Pole. Because that would be going out of the plane and going into the south. Okay? Now, why is this useful? See, what's the point? Why don't we just use a normal magnet? Well, we can make stronger magnets with this. We can make stronger magnets called electromagnets by bringing a wire and looping it. This is called a solenoid. By looping it around a soft iron core. Now, when we run a current through this wire, let's say we have a current running through the wire, that would cause a magnetic field. And what do soft irons do? They absorb magnetic fields. So we'd have a very strong magnetic field inside here. Oh no, that's very unclear. Wait, let me use a different line. Guys, blue is going to be the magnetic field lines, okay? We'd have a very strong magnetic field in the wire, inside the solenoid itself. And here we would have a strong magnetic field, and we can vary the strength of it. So it's more useful than a normal magnet. We can vary the strength of it by maybe increasing the current. Increasing current. Increasing the number of loops. Increasing, I don't know. Yeah, basically that's the only two ways. And it's also useful because we can do what with it? We can turn it on and off. Let's say you want a magnet or whatever. It's useful because it can be turned on and off when you need it. And if you don't want it to magnetize anything, you can just turn it off, right? So that's nice and useful. Now, electric force, electromagnetic force. Right? Here, what if you have both a magnetic field and a current in a wire? So there's this experiment they used to prove it. There was a wire with a current running through it inside a magnetic field. This is like a long horseshoe magnet. It goes like this, okay? So I'm just gonna draw the north and south pole. Well, it's so unclear. Let me use different colors. Okay. So they would have a north pole above it and a south pole here. And there would be a magnetic field going from the north to the south, and a current in the wire going like this. Right, so the wire now is generating what? A magnetic field, and there's a magnetic field. So these two magnetic fields would react anywhere or whatever and make a force. This force, it causes the wire to move. Now, how do we know where the wire would move? Would it move in? Would it move out? How did it swing? Okay, would it swing like in, or would it swing out? See here, there's another right-hand rule. More right-hand rules, okay? This one, it's you point your thumb, you point your pointer finger and your middle finger. Your thumb goes with the current. So I don't know how to draw a hand. Let's say thumb, pointer finger, middle finger, and then you have the other two fingers. They don't matter. Okay, so this one would be the current I, This one is the magnetic field, B. And this one is the direction of the force. So here, your thumb is this way, magnetic field is down. So thumb, magnetic field. Your pointer finger then would be pointing like into the plane, right? Your thumb is this way, your pointer finger is down. Your middle finger is into the plane. So here, the wire would move into the plane. But like, come on, yani, does the wire just move by itself? Where does the energy come from? Okay, you can't just create the energy to move the wire. Yeah, you can't. The current itself gets weaker when the wire moves. The energy of the current gets used up when the wire moves. The current becomes weaker when the wire moves because you can't just create energy like this. Okay? Now, there's a question about this experiment in the CQDs, number 30. Design an experiment to demonstrate the magnitude and direction of the electromagnetic force depends on the relative directions of the magnetic field and the current. Okay, so this experiment. We already showed how we determine the direction, but how can we show that the current and the magnetic field determine the force, right? Let's say we run a stronger current through it and we can test what happens. If we run a stronger current, the force would move it even more. Okay, if we have a stronger magnetic field, it would also move even more. Okay, so that's basically it. Yani. That experiment to show the magnitude and to show the direction. And I'll also solve question 33 because it's a great question. State the rules to determine the direction of the force exerted by a magnetic field on a current. Yeah, this they might ask about it. Okay, it came in the CA before and it was an annoying question. So the one I just explained, the one with IBF, that's the right hand rule. It's just called Fleming's right hand rule. I forgot who, but that's the right hand rule. Now you have the motor force rule. Okay, you have the current. Let me explain also the motor force rule. Okay, this is right hand rule, the first one. Motor force rule is you curl your fingers. So let's say these are your fingers. These are your 4 fingers. You would curl them. No. You would curl them with the current, so they'd start curling this way. And how do I know? Do I curl them down or do I curl them up? You curl them where the magnetic field is going, so you'd curl them down on your right hand. So if you curl your fingers like this, your thumb would be pointing into the plane. This is the motor force rule. Motor force rule. And there's also another one called the right hand screwdriver rule. Basically, you imagine the same thing as the motor force rule. Yani. You imagine a screwdriver going into the plane that rotates to the right. Basically, at that time, all these scientists were trying to come up with new rules just so they can be famous or something. I don't know. Kind of useless. Anyways. Okay, so magnetic flux. Magnetic flux. Okay. So let's say you have a magnetic force. I'm gonna use actually I'm tired of white. A magnetic let's say you have a magnetic force. Okay? These are magnetic field lines going like this. And you have an object. Let's say a plane. This is a wire, okay? Let's say this point is going into the plane, this wire is going out of the plane. So it's basically a wire. It's like this. We're looking at it from this side. Okay, so this side is coming out of the plane, this side is going into the plane. So this is an X, this is a dot. Okay. How do we determine the amount of magnetic field lines going through? How do we know? We multiply the area of the plane, so the area, times the strength of the magnetic field. So times an angle theta, cosine of the angle theta. Well, what cosine of the angle theta? Where's the angle theta? Let's say the plane is tilted. Okay, let's say the plane is tilted. Now, where would the magnetic field lines be? They would only hit this much, the vertical amount. They'd hit the blue, right? That's basically the new area that's getting hit by the magnetic field. How do we find this area? It's cosine, it's the cosine of this angle times the area and the force. So cosine this angle, cosine theta. If they give you this angle, then you use what? Sine theta. Be careful, guys. They might like, this is a trick. They might use this angle. Okay. So yeah, and if it's flat, then cosine theta, it would be 90. It would be, no, cosine this side. Yeah, cosine theta here, it would be like, but yeah, basically cosine theta would be 0 because it's not hitting anything. It's what's it called? Parallel with the magnetic field, so it's not gonna hit. Okay. Now I'm gonna try to solve a few questions. It's not in this quiz, I think. In the next quiz. What was it? 3 point what? Oh no. 3.13 to 3.8. Yeah. Okay, which will double the magnetic flux through the frame. Doubling the area of the frame. Yes, doubling the magnetic field B. Doubling the angle cosine would decrease it. Doubling the sine of angle, oh no, wait. Doubling the cosine of angle theta. Okay? Because that would double what? Oh, no. Wait. No, I wanna, wait, remove this. Okay? Doubling this. This is the cosine of the angle theta. Doubling this would double it. Okay, what's the formula? AB cosine theta. They gave it like this. I don't think they will use this angle, but if they do, use sine. Okay, so you either double this, or you double the cosine of the angle theta. What are the questions here are important? Okay, skip. Magnetic flux is the product of the area and the projection of the, yeah. This is basically just the formula. Okay, galvanometer. Actually, yeah, I need to explain this also. It's pretty important. Okay. It's pretty confusing. So just focus a bit now. Here you have a north pole. Okay. And then you have a south pole. These are connected. Yani this what's it called? Horseshoe magnet. Okay. They're connected. So there's magnetic field lines going from here to here. Okay. Now you have a coil running through this. Okay, it doesn't have to be. It's kind of. Okay, so you have a coil connected to the circuit. Move like connected. Okay, and then from this coil, you're gonna have a pointer, and here there's gonna be like a scale showing like, let's say this is 10 ampere. Okay, it measures current. And let's say here it's in the center it's 0, and here it's 10 also, but in the opposite direction. Okay, so this would be 5 ampere. Okay, so let's say you run a current through this wire. What would happen? An electromagnetic force would either move it this way or this way. It would move it stronger or weaker. It would move it more or less, I mean, depending how strong or weak the current is. A stronger current would move it more, and here this arrow would point at a larger number, signifying a larger current. Okay, but here let's say a magnetic force moves it this way. What would cause it to move back? It would just stay at 10 even if the current goes away. No, here they also have, let me use a different color. Here they also have springs connected to the thing. So if it moves this way, you know, a spring, it bounces back into place. Let's say you extended it like boing and goes back to its place, right? So it would deviate because of a strong current. So it would move, and then the spring is trying to move it back, but the strong current, the electromagnetic force, has it stayed here. When the electromagnetic force is gone, the spring would just point it back at 0. Okay, and if current comes from the opposite direction, the wire would point at the opposite direction. How can you increase the sensitivity? By either increasing the magnetic strength, the strength of the magnetic field, يعني stronger magnet, or here, what you'd have a stronger number. Wait, what? Increase the number of coils. So here, increase the number of coils, more coils. Or you can just use weaker springs, because the springs they pull it back into place. So weaker springs. That's how you would increase the sensitivity of the galvanometer. I think they will ask about this. So the device is called a galvanometer. This device is used to measure a weak current. It measures current because current is what changes the strength of the magnetic field. This drawing is so confusing, okay? And they didn't even draw the magnets, so wait. Here in this device here, you're supposed to have a magnet here and a magnet here, a north and a south. Okay, they didn't even draw it. This is just a bad drawing. I don't know why they used that. Okay. Which of the following would make the device more sensitive? Adding turns to the coil, so more turns in the coil. Using a spring with a higher constant? No, you need a weaker spring. Using a stronger magnet, or reversing the direction of the magnetic field would just reverse the direction where the pointer is pointing. So it's still going to be the same current. So these are the answers. Any more important questions in this quiz? Oh, yeah, the DC motor, I'm going to explain it also. Oh, it's just all DC motor. The diagram where current carrying wire directed rightward. Okay, here just use IBF if it's pointing into the plane. So like this. It's I, into the plane is B. So it's gonna be upward. So wait, okay. I'll just explain now the... What am I gonna explain now? The DC motor. Okay. The DC motor, here you have a magnet. Let's say a north pole. A north. And here you have a south. Okay. And now here you have a wire going through them. Motor, okay guys, look here, because there's some confusion about this. Motor, it turns electricity into a force. Generator turns what? Force into electricity. So here you're not generating current in a motor, you're using the current to generate motion. Okay, so here it's DC, so you have a split ring connected to carbon bushes, carbon made of graphite so they can conduct electricity. Okay, and then here electricity is supplied to the motor. Here you have a circuit or whatever. Electricity is supplied, so now you have a current in the wire, and here a magnetic field. So current, magnetic field, what is it gonna cause? It's gonna cause an electromagnetic force. How do you find the direction? I, B, F. So here this one, we can use IBF. So I pointing towards U. B is going from north to south, or I, B, F. So this one would rotate up, this side would rotate down, and then right, it's rotating. So when it reaches here, wouldn't this side be like supplying north? So this side would be going up again? No, that's why it would split. The sides switch. Like let's say when it's about to go like like this again, because this side is connected to the north. Remember, it goes up. So if it goes here, it would still be going up if it wasn't split. But it's split. So when this reaches here, it's now connected to the other side. So the current also switches direction. Okay, now I'll solve a few questions about this. The device shown is a electric motor or DC motor. And this is what split ring, and this is the carbon brush. Is there any more questions? Okay, the device shown is the DC electric motor. Side of coil A would move. Okay, so this is north. Wait. This is north, this is south, so it's going like this. So this is the magnetic field. I is going this way. So I, magnetic field going from north to south. So point your finger like I can't show you because I'm using my hand to this. So the force would be upward. Okay. Now that's basically everything for chapter 3. Chapter 3 and chapter 4 are basically the same thing. Chapter 4, guess what they talk about? Electromagnetic induction also. But now, yeah, let's talk about chapter 4. What is the difference between chapter 3 and chapter 4? Chapter 3, they talk about force being produced. Chapter 4 is about current being produced. Current being produced. And chapter 4, it goes more in detail. It talks about Lenz's law, Faraday's law, all this, and there's an equation. It's very important. Okay? So, yeah. Yeah, okay. Wait, no, I didn't want to erase that. Wait. So here, for chapter 3, when you use the right hand rule, when force is being generated, current generates a force. So you get force at the end. You use I, B, F. When current is being generated, you flip it. Oh, no, what? Wait, I'm confused now. I confused myself. Wait, what? Yeah, when chapter 4, when current is being generated, you use F, B, I. Why? Because current, it opposes the force. This is Lenz's law. Current opposes the force being generated. Okay? And by current, we mean the flow of positive charge. Positive charge. Wait, there's a question in the quiz that's very important in 4.1. 4.1. Question 14, I think. Yeah, this one. Guys, this one. It's a positive charge, so you use... Guys, here also what? The current is moving. So the current is generating a force. So the force is being generated at the end. Okay? So use IBF. Because the force is being generated. So I, B into the plane, F, the force is going to be to the left. Leftward. But, wait. What if... I don't want to erase... Okay, actually. What if this was a negative charge? Forget the positive. Oh. What if this was Q? What if it was a negative charge? So if it's a negative charge, then you flip the I. Okay, let's say if it was a negative charge going this way, then you'd point your thumb down because the positive charge would be going that way. They asked a question about this also. So it would be the opposite. I, B, F. If it was a negative charge, it would be going to the right. Oh, okay. Now, when is a... Can I open the black? Okay. When is a current induced? When do you get a current? Well, there's a formula for that, and it's very important. Current, or the induced EMF, is equal to negative N delta pi over delta T. Okay, this is the voltage, which is also, yeah, it works both ways. Okay, the current also. So here, the negative sign, this is Lenz's law. is law. This side is Faraday's law. So Faraday talks about the strength, and Lenz talks about the direction. Okay, we guys should know this. Okay, so read this. Okay. Now, let's say you have a wire, a solenoid. Okay. And here you have a galvanometer measuring the current, big G. Okay, I don't even know how to write a G, okay? What's this? And then here you have a magnet, a north pole. Yeah, I have the south pole also because it's going to be a straight bore magnet. So, if you have the magnet here and you just put it near the thing without moving, you just put it near it, would you get a voltage? No, you wouldn't. Delta phi, by the way, is the change in magnetic flux. So no, you wouldn't. If you put it near it, you wouldn't get anything. But if you go near it and you start moving the magnet, start moving it, then you would get a voltage, because then magnetic flux would be changing, right? How can you increase the voltage? How could you increase the voltage? Okay, by using a stronger magnet, increasing delta phi, increasing the change in magnetic flux, or moving it faster, decreasing the time, or using more turns in the coil, right? But guys, this is very important. They might ask about this. If they're both moving together, so let's say this is moving at the same direction, so they're not changing with respect to each other, there is no induced EMF. Okay, there is no induced EMF. Okay. Wow. Okay, now let's talk more about the negative sign. This is Lenz's law, very important. A lot of people are confused about this. Let's say you have I don't know which one is it. Okay, a place with magnetic field going through. This is not a wire. Actually, let me erase this because there's no point in the score. Okay. Here, let's say you have a magnetic field. The bunch of fields going into the plane. Okay. Let's say you have a wire, right? This wire is like it's naturally placed like this. Let's say you move it like this, right? So when you move it like this, the new position of the wire is going to be like this, right? You moved it into the magnetic field. So is there a change in magnetic flux? Yes, magnetic flux increased. So we know that magnetic flux, or phi, increased. So would the current be that's generated try to decrease it or increase it? Here we have a negative sign. So the induced current would try to decrease the magnetic field. So the induced current, so now I have a current, it's going to try to decrease the magnetic field, right? Yes. So if you want to decrease the magnetic field, what would it do? It would create one in the opposite direction. So here it would create a magnetic field in the opposite direction. So you'd use FBI. Wait, what? No, here it would be confusing because you have all four directions. Okay, let's just stick with this. Current would decrease phi. So it would create a magnetic field in the opposite direction. A current that would create a magnetic field out of the plane, we can use the grip rule, because this is a wire, right? We can use the grip rule. We wanted creating a field out of the plane. So curl your fingers towards you. Okay, curl your fingers towards you. And then see where your thumb is pointing. Here it's pointing here. And here, point your finger yeah, from any direction. If you try to curl your fingers towards you, you see that here it's going down, here it's going like this. So here it's going what? clockwise, I think. Wait, no, this is counterclockwise. Yeah, he is going counterclockwise. Okay. Now let's say another case. Let's say you try to pull the wire out. Let's say this is the wire naturally. Okay, wait, let me erase this bit. I hate how it erases everything I write when I use erase. Let's see here, and you move the wire this way. Okay, so now there's no magnetic field in the wire. You moved it out. So phi in this case, it decreased. So the current would want to increase it. It's opposing the change. Opposing the change here, negative. Okay, so it would create a magnetic field going into the plane. Now try to curl your fingers away from you. No matter where you curl your fingers away from you, okay, so now this would be going up. Wait, what? No. I'm still curling my fingers towards. Guys, don't get confused with the right hand rule, yeah. Fingers are going into the plane, so curl your fingers away from you. Here it's going down. Here it's going like this. Here it's going like this, and here it's going like this. Okay, don't get confused with the right hand rule. Okay, also more cases because it's very confusing. Let's say, but this one's simpler. Okay, let's say you have a wire here, and you squeeze the wire. Let's say it's a bendable wire. You squeeze the wire. So now the flux in the wire decreased. So you'd want to increase the current. So the force would basically try to stretch the wire. Okay, force trying to stretch it back. So the current is gonna also go if you decrease it. So wait. Yeah, you squeezed it, so you decreased phi, so you increased. So the current will try to increase phi. So you'd also do the same thing. So it's also gonna be going, try to go into the plane. So current would be going like this, and if the opposite, if you expand the wire, you pull it apart. Okay. Now I want to solve question 7 in this quiz and question 18. So this question, very important. Okay, yeah, erase all this, remove the whiteboard. Okay, the formula, guys, remember T equals negative N, N is number N, N, delta phi over delta T. Okay. Oh, okay, what? Okay, so here we push this towards this. So this is the new wire. So delta phi, what happened to it? It decreased. So the current would want to increase it. So it would make more magnetic field into the plane. So curl your fingers away from you. Away from you. So here it's gonna be going like this. Okay. The induced current flows from B to A. And here the rate of flux change through the loop. Okay, guys. Wait. This graph is showing the rate of flux change. A metal rod can slide along the piece of okay, what does the graph show? The graph of the induced EMF versus time. Okay, so it's showing you the induced EMF. This is positive 30. Right? This is positive 30. And they want to find delta phi over delta T. Here, it's one loop, right? It's not a coil, it's one loop. So plus 30 equals negative 1 times delta phi over delta T. So it's just going to be negative 30. Okay, this and question 18. This one. Here, you move the wire into the plane, right? So here, you would point your thumb. Here, what delta phi increased, right? Delta phi increased. So the current would try to reduce what? Reduce the phi. So point your thumb away from it. I mean towards you. Here, point your thumb towards you, because that's where the magnetic field is going. The generated magnetic field is going. And then curl your fingers. Your fingers are gonna go like this. Right hand rule. Okay. So this is going counterclockwise according to Lenz's law. Okay. So basically, guys, Lenz's law is you have a current. I mean, you have a magnetic field. It's either gonna increase or decrease. Okay. If the magnetic field decreases it, then you want to strengthen it. So you want a current. The current will generate a magnetic field going with the original one because it decreased. It wants to bring it back out. Also wants to strengthen it. Or you increase the magnetic field, so it wants to decrease it, so it would go in the opposite direction. Okay? This is kind of confusing. I'm starting to get confused with what I'm saying. Okay. Now, very important also, another thing they like to ask about a lot is the AC and DC generators. Okay, this chapter, current is being generated. So it's a generator. Okay, let's say here you have north, here you have south, and it's the same setup as the motor. Same exact setup. You have the wire, and here, but it's not a slip ring. It's not a split ring, it's a slip ring. Okay, this wire is connected to this ring, this wire is connected to this ring. The only point of the ring is to not get them tangled. But here this rotates. Okay, this wire rotates. There's change in the magnetic flux. So what's gonna happen? There's change in magnetic, so it's gonna produce a current. So the current here is gonna be increasing, and it's gonna be decreasing, and then it's gonna flip. But here it's not gonna flip. Like this side is not gonna flip, this side is gonna flip. So current is gonna be increasing, then decreasing, then it's gonna go negative. Decreasing, then increasing like this. With accordance to a sine graph. And I feel like I should draw this better because I don't know how to explain this. Okay. Forget that split the slip rings for now. Okay, let's say cool. Now, when the coil is parallel, this is the magnetic field. Okay, I'm gonna draw the magnetic field with red. This is like the same thing. I'm just zooming in. Okay, zoom on the coil here. Let's say the coil is parallel to the magnetic field, so it's changing like this, right? So the rate of change of flux going through the wire here is what? Delta phi over delta t is what? Is a maximum, right? Delta phi over delta t is at its maximum. Okay, and what? Okay, and if it's vertical, then it's changing parallel to the magnetic field. So delta phi over delta t change, the phi over delta t change is equal to 0. And this kind of makes sense if you think about it. Delta phi over delta t is basically the derivative of how much flux, the change on flux per time, right? And we know when the change is 0, when the derivative is equal to 0, that means there's the most flux going through it also, right? So here there's the most flux going through it, but the change itself is 0. So here, when delta phi over delta t is 0, this is max flux going through it. So it's the maximums and minimums. But when delta phi and delta t is at its maximum, the thing itself is changing at the highest rate. So this is phi, okay? This is phi, not delta pi over delta t. Delta pi over delta t here is when it's equal to 0. Okay. So I hope you guys understand. It's a bit confusing the start for me also this part, but this is what you need to know. When it's parallel, the rate of change is the greatest. So delta pi over delta t is the greatest. When it's perpendicular, so there's the most delta pi itself, the change is 0. I hope you guys understand. Also, there's some questions that kind of, yeah. You guys should know also, there's this thing they ask us called the root mean square. Basically, you do the maximum value, so the amplitude, over radical 2. Okay, that's basically it. And if you want to find some questions they ask about finding the period, you divide the, they give you like a sign equation in the question. I'll show you what you divide by 2. Here, this question is important. They ask which generator illustrates an alternating current, which generator is a direct current. So now these generators, it's basically the exact same setup as the motor. Okay, here, but here you spin the wire to produce electricity. Here, in the other one, you use electricity to spin the wire. An alternating current is gonna be the slip ring, so generator A. The direct current, so current in one direction, is gonna be generator B. Now here, question 9. Okay, yeah, this is what I want to explain. So the root mean square, you just do okay. Root mean square, you just do 14.1 over radical 2. Okay, so 14.1 over root 2, you get 9.97. so basically the nearest whole number, so 10 ampere. And it's 16 pi, you divide it by 2 pi, you get 8. Okay, you just divide the thing by 2 pi, sine graph, so 8. Yeah, okay. And question 15, they ask you what's the frequency, so you're just gonna do 45 over radical 2, you're gonna get 31.2, or did I just want it in 32? Let's say it. Or you get 31.8, I mean, so 32. Oh no, they just want the peak value. So peak value is 45, guys, be careful. Root mean square, you divide by radical 2. Now here the frequency is 18.8 over 2 times. You're gonna get like 3 hertz, which is very low frequency, but yeah. Okay. Oh, I'm tired of explaining. Okay, now eddy currents. Eddy currents, basically, what are they? They are currents that build up when you're rotating a disk that oppose the motion of the disk. So let's say here you have a disk rotating around this line. This is a pole, like a metal disk. Okay, so it's rotating, right? And let's say we put it in a magnetic field. So here there's force of the disk rotating, and there's the magnetic field, right? This is the magnet. Okay, this is north, and this point is south. Okay, so you have the disk rotating, so there's a force, and then you have also a magnetic field. So it's gonna cause currents that oppose the motion, so it's gonna cause it to slow down and eventually stop. This is called damping. Sometimes we want to stop this. This is a bad thing. We want to stop it, so we put like holes or little slits to prevent these currents from being able to build up. Okay, So this prevents eddy currents. Well, I'm not gonna go in detail about it. Also, one more thing, it's a bit useless. I don't like it. The oscilloscope, and I don't think they'll ask questions about it. Basically, it just shows you a sine function on the graph, and it just shows you the graph of the induced EMF. How does it work? You have this is the end, like this is where you see the graph. You're looking at it from here, okay? This is your eye. You're looking at it from here, okay? Behind here, there's a whole confusing setup that you don't need to know about. Cathode, I don't even know what happens here. Basically, you shoot an electron at this. It shoots an electron. This is a luminous surface. It lights up when electrons hit it. And then you have vertical planes that cause horizontal deflection. I mean, these are horizontal planes. They cause vertical deflection. These are horizontal. Wait, I'll draw them here. Horizontal, and you have vertical. Okay. Okay, it's kind of hard to draw, but look. Basically, the point is, the electron is going through this. So these are horizontal. They put it either this way or this way, right? They're either gonna move it this way or this way. So the horizontal ones cause vertical deflection, and then you have vertical planes. Okay, it's vertical, and the thing it's going through them. Okay, it's either gonna go towards this one or this one. So it's gonna move it right or left. So the vertical planes are gonna cause horizontal deflection. So it can move up, and then it can move. Let's say it passes through the vertical planes. It's gonna go right or left, and then it's gonna hit a point. These are based off the like amplitude and whatever to show you the sine graph of the induced EMF. But I don't think they'll ask about it. It's a bit useless. Also, the bicycle dynamo. I don't think they're gonna ask about it. Yeah. Now let's move on to the important stuff. Now what they're actually gonna ask about is the transformer. Okay, let's focus on that. So you have an alternating current connected to a coil. All right. Now this coil is connected to a soft iron square. That's what it looks like. Square. And then here you have another wire. Now what does this transformer do? Okay, so now here you have an alternating current, right? What does this alternating current do? Changing current, or current in general, causes a magnetic field. Now because this is an alternating current, I'm gonna use blue for the magnetic field. It's gonna cause a changing magnetic field. So this alternating current is gonna cause a changing magnetic field. Now this changing magnetic field is gonna travel through the transformer. Now what is it gonna do? Now you have a changing magnetic field, and you have another wire. So changing magnetic field in a wire, what does that cause? That causes an induced EMF, right? So, and they have to have a different number of loops. Why? Because then you know how it's negative n delta phi over delta t. So basically to change the voltage. Okay. So if the number of loops, by the way, if the number of loops goes up, n goes up, then voltage goes up, and it's a step up transformer. Step up. Here, number of loops goes down, then the voltage goes down, then it's a step down transform. Okay, and the formulas for it are V out, the output voltage, over Vn equals number of loops coming out, a number of loops in the output, over number of loops in. Okay. Oh yeah, guys, it's called primary coil. This is primary coil. This is secondary coil. Okay. Now what about the current? Current is the opposite. It's not out over in equals out over in. It's in over out equals out over in. Why? Because obviously a transformer can generate power, can generate energy in general. P, and we know power equals I times V, right? So IV in is gonna equal I V out. So let's say I in V in is gonna equal I out V out. This is only for a no, not this. This only for ideal transformers. We'll talk about that in a bit. So this is only for ideal transform. So let's say you take I here, so it's gonna be I in over I out equals, and let's say here you take V in here, so it's gonna be V out over V in. So they're inversely proportional, okay? And obviously you can substitute whatever you want from N out. N is the number of turns, and V in and V out. Okay, why do we use them though? Well, the reason we use them is because, you know, let's say we're transmitting energy or power, electric power, across long distances. Okay, so we would lose energy if we transmit it at a high current, because you know P lost, the energy lost, equals R I squared. So if we decrease the current as much as we can decrease the lost power as much as we can. Now, how do we decrease the current? Obviously by increasing the voltage, since they're inversely proportional. So we increase the voltage as much as we can when we're sending power across long distances, so we don't lose energy. Okay, now when is a transformer ideal? When its efficiency is 100%, it doesn't lose power. Power out over power in equals 1. Okay, so this is when it's ideal. But power out over power in times 100%, I mean, they always want it as a percentage. Okay, times 100%, that is the formula to find the efficiency of a transformer. Okay, so if it's equal to 100%, if it's 100% efficient, that's an ideal transformer, which don't exist. If it's anything less, it's not. Okay, now also this iron core, we insulate it a bit. It's a bunch of like metals, and they, like a bunch of metal squares, yani, and between the layers, let's say these are 2 layers, between them there's an insulating material. Why? Why are we insulating? Because see, eddy currents can build up in it. I know it's not moving, but this current is generating electricity, and you know, we don't want eddy currents messing with it. So we'd insulate it to prevent the eddy currents from building up. Okay, this is basically everything you need to know about transformers, all of this. So you guys can take a screenshot if you want. And one more thing, actually I'll explain it later when we get to it. Okay, so I want to solve CQD number 33 in chapter 4. Chapter 4, 30. Good. Yeah, this question. Okay. A transformer consists of 2 coils of wire wound on a laminated metal core as shown in the diagram below. Explain why the core of the transformer is laminated. To prevent eddy currents which would mess with it. Use the information presented in the diagram to determine the output voltage of the transformer. So, oh no, wait. Let me use the red. So V out over V in, V out, which is what we need to find, over V in equals N out, number of turns out, so 40 over number of turns in, so 40 over 600. 100, what's V in? 240. Okay, let me just do it on my calculator. Oh, good. You get 16. So V out equals 16. Okay, 16 volts. Well, guys, by the way, V out over Vn is called transformation ratio. If they ask what's the transformation ratio, okay? I'm not gonna write it out, okay? If they ask what's the transformation ratio, it's V out over Vn. Assuming the transformer is ideal, what is the current through the light bulb? So you do V out over Vn. Okay, V out over Vn equals In over I out. So V out, so we got it 6, was it 16? I forgot what I raised. 16, okay. 16 over Vn, so 240 gives you 0.05 over I don't know. Let's do the, let me do it on my calc. 16 over 240 equals 0.05 over x. .75. That is the current through the bulb. This is the bulb, it's the output current. 0.75. Okay. Now I want to go to the 4.3 to 4.5 quiz. So 4.3, no, 4.3. Question 3. Oh, this one's the one we just did. Okay, so this is primary coil. This is the laminated core. This is the secondary coil. The process by which a change in current in primary coil causes a change current in the secondary coil is called electromagnetic induction. Frequency stays the same. Oh yeah, good thing we solved this question because I forgot to mention it. Frequency stays the same. Question 4. But it's just the same question. Oh, the last one is the transformer. Assuming no power loss, you just do the formula. So 800 over 50 equals 120 over x. So you get let me do it tomorrow. Give me 2 seconds. So 800 over 50 equals 20 over x. You get 1.25. So I put 20 over x instead of 120. Wait, 120 over x. You get 7.5. 7.5. A 60 volts direct current. Okay, so the bulb will go off. Okay, direct current means the magnetic field is not changing, so there is no like, yeah, it doesn't work. One more question. Oh yeah, wait, one more thing. If the number, oh, they already explained, number of turns goes up, it's a step up. Number of turns goes down, it's step down. Okay, it's step up, step down. What's the number of turns in the secondary coil? Okay, so we're gonna use the formula again. So 240 is what secondary. So 240 over 48 is equal to 60 over x. So 240. No, wait. No, wait. 60 over x. Or no, I mean x over 60. Because this is out. Secondary coil 240. So this is out and this is the primary coil. So yeah. You get 300 turns. The input power of the transformer. So you do P equals I times V. P equals I V. So 4 times 48, so 4 times 48, you get 192. 192 output power, so 240 times 0.72, 240 times 0.72, you get 173 or 172.8, so basically 173. What is the efficiency? So it's 173 over 192, which gives you 90%. Okay, now step up transformer and solve question 1. I'm not gonna solve this part. We don't. I don't want to make the video long. So the number of turns in the primary coil is 100, secondary coil, so it went up. So it is a step up. Step up. And question 11, it should also be the same thing. Yeah, number of turns went down, so it's step down. Okay. Okay. Now what else? Oh, okay, yeah. Question 6, I need to explain it. Or not explaining, just tell you guys. Okay, so the reason we use transformers, as I said, is so we don't lose power. So, but you guys need to memorize the national grid. Okay, so power station, it's 25 kilovolts. And then out of the power station, they can just give you the electricity straight to your house. It has to go through the super grid at crazy 400 kilovolts. Well, it's 400 kilovolts would like melt you in 2 seconds. Okay, and then here your transformer, you push it up, and then the rest are step down transformers. And then in the normal grid, it's 132 kilovolts. This is grid 132 kilovolts. Step down, and then another step down to heavy industry. Heavy industry. So that's 33 kilovolts. And then light industry. Light industry. Light industry. 11 kilovolts. So step down to 11 kilovolts. 11 kilovolts. Light industry. And towns. And then houses and farms or 240. Okay, houses plus farms 240 volts. Okay, so 11 kilovolts, 11 kilovolts. Oh no, yeah, 11, 33 kilovolts, and the super grid 400 kilovolts. An electric device that changes the voltage between different parts of the national grid is a transformer. Transformer. Okay, and last thing is a fuse. Question 15. The way a fuse works is, let's say you have wires in your house throughout everything. Okay, you have wires. So this wire, what if it goes through a fuse? Okay, what's the point of the fuse? It protects you. Let's say the current is so high and you don't want it to be dangerous and you want to protect the rest of the current. So this fuse, you put it here. Let's say it goes this the rest of the current. Okay, this the rest. It's before the current. So let's say the current starts getting too high, then it's gonna melt and it's gonna sacrifice itself. This is gonna melt inside the. Like, this is gonna melt then. And it's not gonna connect to the rest of the circuit. It's gonna disconnect before the rest of the circuit melts. So it's weaker than the rest of the circuit, but it like sacrifices itself. Okay. So it would be here 4 ampere because you want it higher than normal functioning because you wouldn't want it to break for normal functioning, but you still want it to protect, so not too high. Okay. Actually, one more thing before we move on to chapter 6. You need to know the live wire, live, neutral, and earth. Okay, You need to know their colors and what do they have. So live, it's either red or brown. Neutral, it's either blue or black. Earth, it's yellow. So let me use yellow. Yellow. Or green plus yellow. Okay. Now, live wire, it has resistance. I mean, not resistance. What resistance? It has. Yeah, it does have resistance. Every wire has. I mean, that's not like the main thing. It has voltage and current. So it has power. That's the one that powers all your appliances. Neutral, it only has current and it's there, so there's a potential difference between the live wire and the neutral wire. So they both need to be plugged in. It causes the potential difference. So basically, it helps the live have the wire. Its voltage is near zero or zero. Earth has nothing. It's there for protection only, and it has a very low resistance. Why? Let's say this is your, well, I don't know. They use the washing machine in the book. Let's say this is your washing machine. Okay, you have wires and whatever happening inside. Let's say, but the outside of it is metal, so it's conductive. Let's say one wire goes loose. Oh, now there's electricity flowing through this. If you touch it, oh, you get electric. Done. Okay. Except there's an earth wire connected to the ground to like take the energy there and yeah, gets rid of it. So what does it do? The power goes through it, the voltage, the current, everything. I use this. The voltage goes through it and it gets earthed. But it must have a very, very low resistance. Extremely low resistance. Because current takes the path of least resistance. So extremely low resistance. And yeah, that's basically it for all of chapter 3 and all of chapter 4. Now, let's talk about waves. Last thing, waves. Oh my god. Okay, let's go. What is a wave? So first, you have two things. You have a pulse. Let's say you have a rope, and you're holding the rope. This is your hand, okay? You move your hand up and down. So the rope would go up and down once. This is called a pulse. Okay? Now a wave is just a bunch of pulses. Let's say you move your arm up and down, up and down, up and down. This is a wave, okay? Up and down, up and down, up and down. Okay? So pulse, wave. Wave is just many pulses. Now there's two types of waves. You have transverse waves like this one, and longitudinal waves, like for example sound waves. Longitudinal waves, the particles, they don't vibrate up and down. See how here you moved your hand up and down? This is transverse. Transverse. Because you moved your hand up and down. And here, the particles would move back and forth. So back, you'd have rarefaction. And you'd have compression, where there's a lot of particles pushing each other. And the rest is normal. Okay? So, yeah, this is what did I say? Longitudinal waves. Now the waves move particles. Like let's say this is an ocean wave. Okay, let's say I put a ball here. Would the wave push the ball this way? Like the wave's moving this way. Would it push it this way? No. That's not what would happen. I want to draw next. No, that's not what would happen. What would happen is, same way how you moved your hand, you moved it up and down and then back into place. What would happen is the ball would move, or here it would move down first because the down is in front. The ball would move down, and then here this part to push it up, and yeah, that's it. Moves down and then it moves up. And then yeah, okay, that's it. Now here with these longitudinal waves, for example, in air, you have high pressure in the compression, high pressure, and in the rarefaction, the weird word. It's not refraction, not reflection. No, rarefaction. Okay, rarefaction. Okay, this is low pressure. Now, if we do a pressure time, like pressure versus time graph, this time, we'd have high pressure, low pressure, high pressure, low pressure. High pressure, this is the compressions. Low pressure, this is the refractions. Rarefactions. High pressure, compression, low pressure, rarefactions. Okay? And also, what's it called? Like, let's say, never mind. Let's just do the questions. So, chapter 6, so 6 point, where's 6? 6.1 to 6.5. Question 2 and question, is that 7 or 10? I can't read what I have. Question 2. Okay, sound waves are longitudinal mechanical waves. It needs to travel through a medium. Okay, look, guys, you have. Okay, wait, let me just erase this. You have mechanical waves, like sound waves, where particles push each other, like sound waves, or electromagnetic waves, which are always longitudinal waves. Okay, electromagnetic or longitudinal, that can travel through a vacuum, like light. What else? Yeah, light. Okay. Okay, question 10. No, yeah, this one. Okay. Where particles of the medium are spread out. This is rarefaction. When they're together, that's compression. Compression. Which point represents the description in row A? So which point is the rarefaction? Z, because it's down. Which point represents B? So which point represents compression? X. Okay. I also want to solve question 8 in the CQD for chapter 6. Question 8. Define sound waves. Yeah, sound waves are longitudinal mechanical waves which need a vacuum. They're gonna ask about this in the exam. They will ask about it. Okay. Does the speed of waves. Okay, what? Oh, yeah. Look. The speed of waves does not change if it's traveling in a constant medium. You guys need to know speed of waves does. Okay. Speed of waves does not change when you're traveling through a long medium, but sometimes the amplitude can decrease if the medium absorbs the energy. Like for example, let's say you have water, okay, something filled with water. Let's say like a pool or something. Let's say you throw something in the pool. You'd have a big wave and then like smaller wave and smaller wave, and basically like the wave as it moves through, it gets weaker. Okay, as it moves through, it gets weaker till it's gone and the pool there's no waves in it again. Okay, now let's talk about the speed of waves. Let's say you have a displacement time graph. Displacement is like displacement is like here in displacement they don't mean like the wavelength or whatever. Let's say you have a ball here and it goes down and up. This is what they mean by displacement. Okay. Displacement versus time graph. And guys, here you need to be very careful about this. Time. So here you have a wave. Okay, and it goes on. Okay. Now, displacement or amplitude, they mean the same thing. Vertical. Anyways. So here, what you need to focus on is In a displacement time graph, this, okay, focus here. What is this? What is this? Wavelength. No, it's not wavelength. This is a period. Okay, this is the time it takes to cover one wavelength. Because this is a displacement time graph, not a wavelength. Okay? And also you can get the frequency from this because you can do 1 over the period. Wait, what I write equal? 1 over period equals frequency. Okay? A frequency is basically waves per second. Per second, and its formula, or its what is the unit is hertz. So since a period is the inverse, it's seconds to cover one wave, so it's seconds per wave. Okay, now we need to know the equations for a wave. So we know speed of the wave, that's what we need to know. We have this one, and we also need, oh yeah, also period is 1 over frequency. It works both ways. Okay, so speed of a wave. Okay, we know that speed equals distance over time, right? So here, what's the distance of a wave? What's the velocity of a wave? It's wavelength, so the distance over the time it takes to cover one wave, so over time per wave, so second. What's it called? What second? Period, okay? So we have velocity equals wavelength over period, or you can use frequency, so velocity equals wavelength over 1 over period. So no, not over 1 over period, what am I saying? Times frequency, okay? You do times frequency, wavelength times frequency. Okay? Now let's go to the quiz, and we need to solve some questions. Question 11. Frequency is the number of cycles, so waves per second. Speed is what's it called? Distance traveled per unit time, distance over time. Amplitude is the maximum displacement of a particle from its rest position, and the wavelength is the length of a wave. Easy, common sense. And question 5. Yeah, okay. This is a displacement time graph. So here from like peak to peak, it's not gonna give you a wavelength, it's gonna give you the period. So here, what is it? I can't give it back. From what? From what? From here to here. It is 0.1 to 0.3, so 0.2. Okay, wait to see. Is it 0.2 or am I like? It's 0.1, this is 0.3. Okay, yeah, 0.2. And frequency, you just do 1 over 0.2, so 1 over 0.2. You get 5 hertz, pretty low frequency. And the amplitude of a wave is from 0, so from here, this line, to its peak, so, or to its bottom, let's drop. So what is it? 1, it's here, so it's 1 point something, so 1.1, 1.2, yeah, 1.2. 1.2. Okay, that's it for this quiz. Can we finish? I'm actually tired of talking. Oh, okay. Now, the intensity of a wave, or like let's say a sound wave, how loud would it be? Let's say, again, here we have the graph. The intensity of a wave is its amplitude. Let's say you have a, oh no, that's a terrible wave. Let's say you have a wave like this, and another wave like this. Which one's louder? This one, the bigger one's louder. So amplitude, I'm just gonna say amp, or it doesn't matter, equal intensity or strength of the wave. So louder, brighter light, whatever, okay? And what else? Frequency in a sound wave, frequency equals the pitch. So a high pitch, high frequency. Okay, and what's it called? Similarly to magnetic field lines, waves you can't have two waves at the same place at the same time. Okay, there's also superposition in waves. Let's say you have a wave like this and another wave like this. This is going towards this. This is going towards this. This has an amplitude, a positive amplitude, has a positive amplitude. They would add up. They would give you this, and then they would separate again when they go past each other. This one will continue moving this way. This one will continue moving this. So this is gonna be like double. They're both the same thing. Okay. Now, what if one's down and one's up? This one's going towards this. This one's going towards this. It's plus. This is minus. And then let's say here they would cancel out. Okay. You just add them. Okay. And then they would separate again. You'd have the plus on this side now and the minus on this. But guys, let's say this was plus 2 and this was minus 1. Then you still have plus 1 here. You still have an amplitude of 1 here. You just add the amplitudes. Okay, this question is in the quiz actually. 6.6. Question 16, the last question. Oh no, there was another one also. This is a destructive interference, but there was another question. I forgot where it is. Where is it? Was it before this? Where did they go? Oh, here, okay. Two pulses, amplitude 5 centimeters and 3 centimeters meet at point O. If pulses interfere at O constructively, so they both help each other. Wait, did I say constructive? Oh yeah, look, guys, it's constructive. Constructive. This is destructive. Okay? This is the down is destructive, up is constructive. Okay, so you just do 5 plus 3, you get 8. And if it's destructive, you do 5 minus 3, you get 2. Okay? Now, what's it called? Now, let's say you have a rope. This is the fixed end, a reflection of waves. Yeah. Let's say you have here. Let's say you have a rope with a fixed end. Okay, it's stuck to the wall or whatever this is here. Okay, you're holding the rope. You move it up and you move it down. So you're gonna send a pulse to the wave, right? Let's say only a positive part of the pulse. Okay, so it's less confusing. Only one. Okay, so now it's gonna go travel, and then here it's a fixed end, so it would go up and then bounce back because it's a fixed end. So it would come back as a, like it's gonna go like this, and this is the same rope. I'm just drawing it again. It's gonna come back like this. Okay, this is fixed end, fixed end. And I don't really know how to explain it here, but yeah, that's just what happens, I guess. And here you have a free end. Free end. So the rope here can slide up and down. So here you have the rope, you move it up and down. It's going up. Oh, I need to draw a better arrow. Going up, and then here when it's coming back, it's gonna also be up. Okay, why? Because it's not fixed to the wall. So the wall isn't gonna like flip it, bounce it. It's gonna just though it's gonna move. This part is also gonna move up, down, and it's gonna send it back how it was. Okay. Now one more thing. Let's say you have a wave. It's going from a less dense into I increase this. This is the more dense medium. Okay. So let's say it's traveling to this. Let's say it's traveling from less dense to more dense. More dense acts as a fixed end. This you can imagine it as a really dense rope, as a really dense medium, because it's just thick, you know. Like if this was this thick, then it would be considered a fixed end, basically. Okay. So what's this line? I forgot what I did this for. It goes from less dense into more dense. It's gonna act as a fixed end, and it's gonna travel back like this. And actually, since it's not like actually a fixed end, it's just a more dense medium, this is gonna take some of the force. So here, the amplitude would decrease. So here, amplitude decreases for both of them. Here, amplitude decreases. Here, amplitude also decreases, and it's flipped. Okay? And yeah, now what if it's going from more dense to less dense? Then that acts as a free end. Okay, so you have a more dense. It's going, no, this is supposed to be dense. You have a more dense one. I should draw it more up so I have space to draw the one under it. More dense into a less dense medium. Oh no, this is supposed to be. So this is going this way. And then it's gonna bounce back. But it's gonna bounce back like a free end. And some of it is gonna go here, obviously. So yeah, you're gonna have the free end. But wait. The amplitude in the free end is gonna be greater, because it takes less energy from the wave to move it. This is the only place where amplitude increases. Okay, and here it's gonna bounce back with less amplitude. So here amplitude decreases. Here it increases in the less dense end. Okay? Okay. Now let's move on to reflection of waves in a wall. Like let's say you have a wall or a reflective surface and a wave reflects there. Okay, oh my god, we're almost done. You have a wall, okay? The reflective surface, let's say mirror or anything. You have a wave. Oh yeah, I didn't explain this. Look, guys, if you see a representation of a wave like this, then the peak to peak, these two lines basically they're the peaks of the wave. Peak to peak, this is a wavelength. Okay, this is the wavelength. Length. Okay, sometimes they tell you this distance is 6. What's the wavelength? It's 3. Because this 6, it's 2 wavelengths. Also here there's a question in the quiz. In this one, yeah. So yeah, wait. Okay, here's the stuff in the back. The diagram below represents crests of the wave spreading through the medium. The smallest graduation of the grid is 10 centimeters, so one tiny thing is 10 centimeters. The distance from S to A is 4 centimeters, so this is 4 centimeters. What? That doesn't make sense. How is smallest grid 10 and this is 4? Anyways, the crest A becomes the trough in how many centimeters? Okay, so crest is a peak, trough is the bottom. Okay, so and then crest again, that's the wave. Okay, so if this is what if this is 10 or this is 4, yeah, this is 4. So what's the distance to the trough? It's half of it. It's 2. It's 2. And the crest A becomes a trough, then a crest again. The wave propagates by another something centimeters. So for a full wavelength, so from crest to crest, for crest A to become a trough, then a crest again. So a full wavelength is how many centimeters? So it's basically the distance from S to A. So we can just count the small things. So 10 centimeters, 20 centimeters, 30 centimeters, 40 centimeters, 50 centimeters, 60 centimeters. So 60 centimeters. Okay, now time to go back to the reflection of the waves. Okay, so you have yeah, let's go back to where we were. So you wave hits a wall or a medium or whatever, something to reflect on. How would it reflect? Guys, remember the first thing we took in physics in grade 9? You draw this and then you draw the normal. Reflected ray equals incident. This is incident ray, this is reflected ray. Reflected ray is gonna equal the incident ray and then it's gonna travel like this. This is like you draw a line perpendicular to the wave fronts, so the crests, and then you just have crests like this. Okay, now also this one you should note, you have a source of the sound, and then you have here a wall or something also to reflect on. And let's say the sound goes like this out of the source. Okay, it's gonna hit it, and then how do you know how it's gonna reflect? You draw like a line like this. Okay, and you have a distance here. Okay, this distance, wait, you have the same distance here, the same distance. Okay, then you're gonna have this, and then you draw the same lines, and then the waves are gonna reflect out. So the red is the reflected waves. They're gonna come out like this. Okay, also one more thing. Let's say you have like a concave like lens, or I don't know, concave surface, and you have a source as 2 4. You have a source, it's gonna reflect, it's gonna give sounds, it's gonna reflect sounds to the surface. Now this concave surface, it's gonna have a focal point, so it's gonna reflect all the sounds to here, and then this sound becomes the new source, and the sound is gonna be like loud, very loud here. Okay, not as loud as this thing, of course. It's the loudest, it's the main source, but it's like a new secondary source. Now I want to solve questions 2 and what is it, 6? Question 2 and question 6, and is that I don't even know, I can't even read my hand. Okay, which of the following will happen to the pulse upon reflection? Here, this is a free end. So it's gonna, what happens at a free end? It stays positive. So if the speed of the pulse increases, no, the amplitude of the pulse remains almost the same. Yeah, frequency of the pulse remains the same. Yeah, pulse is not inverted. And yeah, question 6. Okay. Oh no, I still didn't explain this part. Question 9. Yeah, okay. A plane wave strikes a straight reflector as shown below. So here. This wave, oh no, this is white, travels like this. This is the normal. So the reflected wave would travel like this. Okay? Okay, great. Now, guys, we have one more topic. Actually, two. two, almost. Two more topics. Quick. We'll go through them quick. And then, yeah. So, a refraction now of waves. Let's say refraction, so going from one medium to another, can be from less dense to more dense, more dense, less dense. But here they focus mostly on less dense to most dense, especially deep water, which is less dense, to shallow water, which is what? More dense. Why? Look, so let's say here you have deep water and there's water, okay? And then it becomes shallow. So basically what is happening here, the sand and all of this is causing this to be more dense, okay, whatever this is, okay? So shallow water is more dense than deep water. So this is what? More dense. Okay, what happens when you refract? So let's say again, this is the surface you refract. So let's say again you draw the perpendicular to the wavefronts. It's gonna hit the refractive like surface, and then you draw the normal, and then here you're gonna have the incident ray, and then you're gonna have what? The refracted ray. But so why did I draw it straight? It's not gonna be straight. It's gonna like bend, okay? Refracted ray. So guys, also it has the same stuff. Remember N1 sine alpha 1, N2 sine alpha 2, I think, but they won't ask for it. Same as refraction of light. And then the new rays are gonna be refracted and all of that. Now, oh, the last topic finally, and then I'm done. You have something called diffraction. What is diffraction? It's basically sound waves spreading out. So let's say here you have a hole in the wall and you make a sound here. So there's sound. It's gonna hit the wall and it's gonna come out and then it's gonna spread out from the hole in the wall. Okay. So the sound here, it goes everywhere. But here, out of the hole in the wall, it's gonna spread like this. Okay, and obviously the further away you go, the weaker it gets because the amplitude decreases, so the volume gets lower because the air absorbs the energy of the waves. Okay, this is not all. These lines are not all. Like, this is just how the wave goes. Okay. Now, what if you have two slits and the waves collide with each other? Let's say you have a slit, space, and another slit. So let's say I have a wave coming out of here. Okay, and then they would collide, right? So then you would have peaks, and then you let's say this is sound waves. You'd have very loud waves where they collide, and very low waves where it's two like troughs. So let's say here, loud, not loud, loud, not loud, something like that. But also with light waves, you'd have light, dark, okay? It would show like that. This is called diffraction, how it spreads out. And yeah, let's solve a few questions about that. And then, yeah, the vid's over. So, where was that one question I said we still did? Okay. Arago spot is a bright point. What? Arago spot is a bright point that appears at the center of a circular object's shadow. This bright spot is surrounded by several light circles. Okay. So, the bright spot is constructive interference of the two waves, and then the dark is the destructive interference. Arago spot is shown in the left below the magnified image of the Arago spot shown in the right diagram. Okay. Which of the following explains why rays of light change their direction? Well, this is diffraction. What? Oh, or is it refraction? Refraction. I'm gonna say refraction. Diffraction is when they spread, right? Actually forgot. If it's wrong, then yeah. Which of the following best explains the formation of bright spot? This is constructive interference. And question 13. Oh, yeah, you guys need to know this also. Okay, so this I forgot about it, but the last thing. Okay, So basically, you need to know the electromagnetic spectrum. It's easy. It's just memorizing it. There's nothing to explain here. Gamma rays, X-rays, UV, infrared. Oh no, UV visible light, then infrared, then radio waves. Now, these waves here this way. Wait, I want to draw. This way, frequency increases. The other way, this way, than the way they're arranged, wavelength increases. Okay, so the way they're arranged in order of increasing wavelength. Okay, guys, now that should be everything for the physics term 2 final, obviously other than chapter 1 and chapter 2. So yeah, that's it. I'm done with the vid, and good luck on your exam, guys.